All right, I will try to keep this one short and sweet because there's not a whole lot going on in here. So we'll talk about some exceptions in stereochemistry, and then we'll talk about how to separate out enantiomers. Okay, that's resolution. So first of all, exceptions. Okay, for anything that we do, there are exceptions, which is, really sometimes hard. Um, so in case of stereoisomers, the main thing that we talked about before is that all chiral compounds, have to have a tetrahedral, okay, in there. But what happens is in some cases, you will have rings and you will have double bonds that are so restricted in their rotation that they end up having chiral centers even though the carbons are sp2. Okay, so generally you're supposed to have sp3 carbon, but here you have sp2. But again, because of sterically, they have no rotation possible, they're stuck. And because they're stuck, the mirror images will not superimpose, okay, on each other. So that kind of happens over here. Now, how many compounds there are of this kind? There are a few. Generally, people make them only to study them, not because they are any useful practically, for anything. But there are exceptions, and one should always know exceptions just in case you run into anything. And then the other exception, which is not quite an exception, but still, okay, we've talked only about carbon as a tetrahedral, but nitrogen is also a tetrahedral, okay? And nitrogen, the problem is that nitrogen compounds will usually have something like a lone pair of electron on them. So even though you have, let's say a CH3, and I'm going to write a short form because I don't have enough space. So you have an ethyl methyl propyl over here, so which means that you have a chiral center. The fourth group is the lone pair of electrons. Okay, so you have a chiral center here, but because of that lone pair of electron, this tetrahedral, which is the nitrogen, right? Because it's like this, right? That's the tetrahedral, that's the electronic geometry. The shape is trigonal pyramidal. So just imagine something like this as an umbrella where that umbrella will keep flipping all the time. Okay, so a strong wind comes and suddenly you have the flip. And so the nitrogen keeps flipping, or the three groups on nitrogen keep flipping up and down. So which means that, the chirality is not absolute, okay, because it keeps changing all the time. So in order to make nitrogen a proper chiral center, you have to lock in that lone pair of electrons. So the best way to lock in that lone pair of electron is by removing it. And the way you remove it easily is by treating any kind of a nitrogen compound with acid. Okay, so as soon as you treat it with an acid, acid plus base gives you a salt, and that's what this is. Okay, so once you have the salt, now you have the hydrogen that is, bonded with nitrogen for that fourth bond, okay, in there. Now it is locked into position. Now it cannot do the flip-flops, okay, anywhere. So now if you have three different groups on the nitrogen, which it does over here, then, you are stuck in that position. And now this is a chiral center. And actually nitrogen compounds are very commonly used even in chemistry, as in, we're going to do that in a few minutes, as chiral compounds, and in nature also they are very commonly found. Okay, so I wouldn't say this is an exception. It's just that we don't study here so much of nitrogen compounds. We focus a lot on carbon, but otherwise nitrogen as a heteroatom is a very common chiral center. So a little bit about the properties of stereoisomers, okay? And so here I wanted to give you some properties, not that I want you to memorize any of these, but here is a tartaric acid, and then I've given you the properties for the enantiomers and also for the diastereomer, which the diastereomer happens to be a meso also. But, look at the specific rotation for RR and SS, completely opposite of each other, right? That's how it's supposed to be, equal in opposite direction. Everything else is pretty much the same, okay? But for the diastereomers, things are a little bit different. There's no optical rotation because it's a meso compound, but look at all the other properties. They are different from the other set of enantiomers or stereoisomers. So this is just to show you that, different molecules can have different properties, or I should say stereoisomers have different properties, diastereomers. So resolution, one of the last things we have to do is, separation of enantiomers. Separation of enantiomers can be for an equal mixture of R and S, which is a racemic mixture, or it could be not an equal mixture. You still have to separate the R and S. So enantiomeric excess, a word that I have not really used before, is when you have one enantiomer more than the other, but that is when you have an unequal mixture. Okay, so how do you do resolution? How do you separate out chiral compounds, okay, or enantiomers? So you take the enantiomers, which are R and S, and again, equal or not equal, it doesn't matter. Then you treat it with either an acid or a base, which is of one particular configuration, either R or S. You decide whichever you have available, but you choose only one. Okay, so then what happens is that R is going to react with R. R is also going to react with the S enantiomer. Okay, so it will react with both of these enantiomers, and once it does, then you end up getting diastereomers. You get a bond for R and R, so that's one one compound that you get. The R, when it combines with S, you get R and S, right? So these are diastereomers. So now you separate the diastereomers. Now how do you separate them? That depends on the physical properties. So you can separate them by distillation depending on if the physical properties are that different. A lot of times we use what is called chromatography, and chromatography is a little bit a different technique. So chiral chromatography is used a lot to separate out the diastereomers. Okay, and chromatography is based on the interaction of a compound with another phase, okay, a solid phase, and then there's a liquid phase that carries the other thing out. Okay, so it's a lot of phase interactions that we're dealing with. So chiral chromatography can help, or physical properties like boiling points can also help. Once you separate out the diastereomers, then you can go ahead and remove the R, and then you get your enantiomer. Okay, so I think I have this wrong here again. So always I find one mistake somewhere, and so this should be S. Okay, so you have the different enantiomers then. So you can see it's a long process. It's not, a simple, straightforward process, but you have to do resolution if you have enantiomers, and especially if anybody is in the medical field and you're trying to make new drugs, you have to test them both, so you have to separate them out. And here are some resolving agents, which means that, compounds that are used to separate out enantiomers. So it could be a base, which is this, and again, nitrogen here is not nitrogen is the chiral center, but there is a chiral center, but this is the base that's going to react. And then here is an acid, which is also chiral, has a chiral center. Okay, so that's what's important here. The base, the nitrogen doesn't have to be the chiral center. Okay, so there has to be a base, that's all that's important, and a chiral center. And I think that's it. So all these words I've given you is not just for this slide, it's actually for the whole chapter.